Right. Now, you've dealt with electricity last year. We've dealt with all the basic circuits, how everything works, circuit diagrams, calculations relating to circuit diagrams, internal resistance, all of that has been covered. Now we want to cover the section of work on electrical power. Now I'm going to give you, I'm not too sure if you've got it, but a listing of energy equations and power equations. They go together, they're almost identical. Now we need to know that power equals energy over delta time. Okay? Power equals energy over delta time. So if you have any energy equation, all you would do is divide that equation by time and you'll get the power equation. So if we take the first energy equation that I'm going to give you is energy equals voltage times current times delta T. Okay? Energy is voltage times current times delta T. Now, what formula would you get for power that is related to that formula? Let's just have a look. Power, we said, is E over I, so we could say VI delta T over delta T. Do you agree those go? And power would therefore be VI. You've seen that formula before? You've used that formula before. Okay. So power equals VI comes from energy equals VI delta T. There's another energy formula. Energy equals I squared R delta T. Now, where do you think that comes from? We're just going to work here on the side briefly. Where do you think that formula comes from? Do you think we just sucked it out of our thumb? IR. Remember that energy equals VI delta T. But V equals IR. You agree? So if I replace that V with IR, I'm going to get IR I delta T. Would you agree? Which is going to give me I squared R delta T. There we go. Happy with that? So it's not a new equation, it's just I've substituted V equals IR into it. So you may want to just write in here, but V equals IR, therefore energy also equals that. Happy with that? Right, what would the energy equivalent, the power equivalent of this formula be? Power equals I squared R. You're dividing by delta T. All happy with that? Okay. Now, what did we replace in this formula to get this formula? We replaced the V. What can we replace now instead? Sorry? Replace the I. What is I? I is V over R. So therefore, what will that give you? E equals, let's do the calculations over here. E equals VIT okay, equals V. I is V over R delta T. What's that going to give you? V squared delta T over R. V squared delta T over R. Because I all agree with that? And what is the power equivalent? Power equals V squared over R. There we go. You've now got effectively 3 formulas, so it's really one formula and various different versions of it. Okay, all happy? So let's just take away all the by the way stuff. Clear that later. Let's have a look at it. There is our table. And if you just know one of those formulas, you should be able to derive the others. You may want to get out your data sheet and just see which of the formulas is in your data sheet and mark it. This one is in the data sheet, as long as I can derive the others from it. I'm not too sure if your latest data sheet gives you all of those formulae or any of them. And that I want to stress, that when you do your studying, please check every formula that you study. Is it in my data sheet? If it isn't, you've got to learn it off by heart. Let's have a look at the data sheet. Electricity. Yes. You do have something down there where my thumb is. Power equals work over delta time. Now you'll remember that I said to you, work and energy are equivalent. Okay, so you can either have it as power equals work over delta T or our power equals energy over delta T. Then the formula power equals VI. And if you want to go from power to energy, you multiply by delta T. If you want to go from energy to power, you divide by delta T. Right. They've also given you I squared R. That one is given. And they've also given you v squared over r. So each of these formulae are provided in your data sheet. And that one, a version of that one. Okay? These are not. Where? Where? Oh, work, energy, and power. Where? Show me. Oh, thank you, thank you. So they're all provided. Okay. No problem. Everything is in your data sheet. Right. So you don't have to be able to derive the one from the other, but it's often useful to be able to do it rather than going to search for a formula. But the more you practice, the more you'll get used to that data sheet, where to go and look for formulae. Okay, you all happy with that? Can I give you some examples? Okay. Provided I can clear this. Let's see. Okay, start taking down this example. I'll dictate it to you. Start writing. Yes. Yes. Right. Example. You are looking to purchase a kettle. Write down. You are looking to purchase a kettle. One is marked 2 kilowatts and the other is marked 1,500 watts. Notice a small k, capital W. Okay? Right, which kettle has a higher power rating and why? Can anyone tell me which one has a higher power rating? Timon? You saying the kettle with 2 kilowatts. Why do you say that? How many joules of work will that do in a second? It will do 2,000 joules of work in a second. Okay? It uses 2,000 kilowatts. Sorry, not 12,000 kilowatts, 2,000 watts. No, it's it adds 2,000 joules of heat per second. That's what that kettle is doing. The other adds how many thousand joules of heat per second? Please don't abbreviate second like I have. It's not correct. What is the abbreviation for second, please, Thomas? Or second, yes. What is second's abbreviation? S. Capital S or lowercase s? Lowercase s. Basics, 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 Thomas. Okay. Per S, right or right up per second. We've got plenty of time. I just don't have space here. How many volts would each kettle be designed to work on here in South Africa? Which one would work on more volts? Neither. First one. Who's correct? Daniel, why do you say neither? So if it's been plugged into the same socket, the same number of volts have been supplied, your answer? How many volts do you get from a plug point in South Africa? Between 220 and 240. It should be 220, but it can go up, it can drop. So work on about 220 to 240. We normally do our calculations on 220. Most appliances that you buy are designed for 220 volts. Okay, so the answer there is 220. Both. So if they're both plugged into 220 volts, why does the one produce more heat than the other? More effectively designed. Less resistance or more resistance? More resistance. Let's put that down as the next question. Which kettle has the higher resistance? Show your calculations. Well, which formula would you work with? Would you be working with this formula? Well, we're just working with power now, that formula. What have I asked you about? Resistance. So could you work with that one? No, that one you won't work with because there's no mention of resistance anywhere in that formula. That one you can't work with because I haven't given you I. That one, do you have the power? Yes. Do you have the voltage? Yes. Can you calculate the resistance? Come on, baby stuff. Do it. Okay, how are we going to do that calculation? What's your formula? P equals V squared over R. Right. We know, so let's swap that formula around. R equals V squared over P. Do you agree? And our two formulae are, what is V for one kettle? 220 squared over 2000 and 220 squared over 1500. Which one has got the higher resistance? The 1500. The lower the power, the higher the resistance. Make a note there. The lower the power, the higher the resistance. You all with me? Okay, now the question I want to ask is, if I look at these formulae here, why does the one with the small resistance, you agree this one's got the small resistance, it's got a higher power, so it's got a smaller resistance. Look at that, if resistance is small, surely my power should be higher. When you've got a low resistance, tell me about the current that flows through it. It gets bigger. So if I halve the resistance, what happens to my current? It doubles. So the one gets less, the one gets more. But tell me about the current effect. It's squared. So you halve that, you double that, you'd think, okay, it stays the same. But because current is squared, the doubling effect plays more part. So if you can bring your resistance as low as possible, your appliance has as much power as possible. Okay? So you may want to just make a note. Note to the higher the power, the lower the resistance. Note, the higher the power, the lower the resistance. Yeah, so you've got that. So just make sure you know that and you understand that. Things with a high power have got a lower resistance than things with a low power. So D, how much current is flowing through each kettle when properly connected? Can I clear this? Right, which formula are you going to use? P, they're all P. Oh, for D, yes. P equals VI, yes. That makes sense. Yes, you could use either one of them, no problem. Ah. Apologies. Okay, P equals VI, or any of the others. We know that the power of the one is 2000, and remember, notice, do I work with 2 kilowatts? You always work with watts, that's the SI unit, okay? 220 is your voltage times I, therefore I equals, what is it? Give me an answer, please. 9,05. Okay, and what's the other one? 1,500 equals 220 times the current. Therefore, the current equals, what does that come out to be? What? 82 amperes. Okay, which one's getting more current? The high-powered one gets more current. And what did I say to you last year? What is the main thing with all electricity that determines how hot the plate gets, how fast the kettle boils, is the current, not the resistance. And as you can see here, both the current and the resistance affect the power. But the current's effect is squared. Therefore, if you can double the current and halve the resistance, it will work better to give you more power. Okay, understanding that? Right, how much heat energy does each kettle produce in 1 minute? Which formula are you going to use here? Sorry? P equals E over delta T. P equals energy or heat over delta T. That could be an H if you wanted, okay? You're trying to find out how much heat energy. Power is 2000 equals E over 60. E equals, you can tell me what it is. Okay. This is all happy? I'll double check your work in there, okay? I'd like you to take down a homework example, please. Homework example. A 60 watt and 100 watt light bulb are connected in parallel . And plugged into a 220 volt socket. Right, that's your homework. A 60 watt and a 100 watt light bulb are connected in parallel and plugged into a 220 volt socket. Calculate the light and heat energy produced by each. Also calculate each resistance. Thank you. I'll see you tomorrow. Make sure that's done for homework.